Hey, welcome back, folks. We are into chapter 15. We are looking at rigid body motion. So let's get to it. We have an example here, but before we get to the example, we're going to need to talk a bit about what this is all about. So we're starting off with kinematics, right? So in general, we are interested in describing the motion of rigid bodies. And if you think about it, the biggest difference between, say, a pencil and a marble is that you can rotate a pencil, right? So if you have, for example, some sort of a mass like this, it's got point A. By the way, it would be a good idea to take notes on this, just because there's a lot to it. So if you got point A, you got point B, then in this, just random body, then you may have a case where the entire mass is translating, right? And in that case, VA and VB are the same, sure. You may have a case where it is curvilinear motion, right? In which case, A and B may be the same. But more likely than not, you'll have a mismatch, right? So if you can imagine, maybe this object is rotating about point O, well, clearly, because the distance between O and B is larger, then B is going to be rotating about that axis more quickly. And so we are going to look quite a bit at rotation. And we have a bunch of equations to get through and to add to our repertoire, but luckily many of them are going to be familiar, right? So to begin with, let's just talk a little bit about rotation and start with what we know. So in calculus, we learned that if we have some radius r and some arc length s, then the way that s is related to r and theta is very simple, right? It is s equals r theta, arc length. Okay, well, likewise, if we take the time derivative, then we get s dot and theta dot, right? And for our purposes, s dot is v, and theta dot, we can leave as theta dot. It's also referred to as omega. This is not w, this is omega. And the definition of omega is, so 3 bars for a definition. Definition of omega is d theta dt, right? Which we can also represent as theta dot. There's quite a few different ways of representing these, and so it will help to have several just listed. If it's accelerating, that is, so we represent that with alpha. So alpha is, we can call it omega dot, we can call it d omega dt, we can call it theta double dot, which is the same thing as the second derivative of theta. Right, so we've got a lot of ways of representing these, and that's good because we're going to need them. One that we will see sometimes is that we'll also see this relationship. We'll see alpha d theta is equal to omega d omega, right? And we get here using that chain rule expansion that we did with rectilinear motion in previous chapters. Okay, so let's see, we want this one, and this one, and this one. It's really good to understand where this comes from. So for constant acceleration, alpha, we have relationships that they should be very familiar because they're essentially exactly the same as the ones that we derived in particle kinematics. So omega equals omega naught plus alpha t. Should be very familiar. Similarly, theta equals theta naught plus omega naught t, so omega naught t plus 1/2 a, and I'm going to say c on these just so that we're real clear that these are constant acceleration only. You will often be given problems that are not constant acceleration, and it's really important to make sure that you're clear on the difference there. And then finally, with this one, omega squared equals omega naught squared plus 2 times alpha c, and then theta minus theta naught. Right, and these are, in big picture terms, these are ones that should be pretty straightforward. So let's take a better look at this guy here. Okay, so hope you got these. I'm going to erase all the way up to here. Okay, and we need to complicate this a little bit. So let me redraw it because I'm going to expand it, and let's draw this more as a plane, a spinning disk, if you will. So let's define a center and go here, and we'll call this R right here. Okay, so we'll call this one R. Right here, we'll call this here d theta. And what we mean here is that this is, if you go from time A to time B, and it's rotating, then you change the angle by the amount d theta, right? It's just a differential value. And this, I hope this comes through as intended. This is the v, we'll call this the tangent velocity. And you know what, let's put it here, just so that it's a little easier to see that it is parallel to this plane, right? So this is vt. Okay, and this here, ds, right? So again, it's just the differential of the area. We can call this position P, right? And let's now draw a random axis with an I through it, like this, right? And notice that this is our direction, right? So this is the way that we're spinning. Maybe it's a little bit better to have it like that. Okay, and because of the right hand rule, which by the way, just sort of get in the habit of using, then the omega, the positive direction of the omega is there, right? We're going to be doing cross products and such. So if we have this point P right here, then what we can do is we can look from the top And we get what we were just seeing, right? And this is really not a good idea to put this v here. It's so confusing. Let's go ahead and put it here. And just, again, this is the tangential velocity. ds goes in here, right? And it corresponds with r, right? So this is the relationship. So if we're given a 2D plane, that's great, that's awesome. But what if this point P is somewhere in our random thing, right? So here's our axis going right through it, and P is, say, on the edge, or maybe not, right? And it's rotating like this, right? So same situation, except that it has a body now instead of just being some fictitious plane that we've imposed. And note, this can be in any direction. This axis can be in any direction. And so this would be P, right? What we can do is remember that if we look down on this, then what do we have? We have this and this and this, right? So this is V. This is our, what do we call this? Let's call it K. We'll call the axis direction K. It's handy. So this is our axis direction here at the middle. V is going that way, R is going this way, right? So remember that from our moment analysis, R cross F, right, would give us a direction going that way. And then, right, so this is V sub T. Okay, well, we're going to do something similar. And what we're going to do is we're going to pick a point down here, doesn't matter where, and we're going to impose a vector, position vector, okay, from there to there, this guy here, and we'll call this RP, right? It goes to P. And again, looking down, if we look down on this thing, then just notice that R, so this is our top view, right? Top view. Notice that our RP and our R coincide, right? And our direction for omega is this way. So if we think of this in 3D terms, then crossing omega with RP will give us V, right? So the rule is that V is equal to omega cross RP, right? Which we simplify to R in general terms, because if this is true, we can, and we're in the 2D plane, then we can just as easily reverse the direction, right? And say that that's true. Well, if that's true, then it doesn't matter where R comes from, right? We learned that in statics. So this is our relationship to get the velocity, and note, what we're talking about here is the tangential velocity. You'll pretty much always see it just as V, just in the same way that you'll pretty much always see this just as R, but it is the tangential velocity, right? And expect that the problems that are challenging that are going to be complicated. Okay, so back to this relationship with at point P. Well, if this is our velocity in the tangential direction, then our acceleration in the tangential direction is going to be equal to our, I'm sorry, that doesn't even make sense. This is AT, right? Our acceleration in the tangential direction, right? We know that from here. And what is that? That is alpha, right? So whatever this acceleration is here, right? And just notice that omega, there they go, same direction, and that would be r, right? So this is in the 2D plane. In the general sense, we'll get to that in a second, but 2D, an is equal to omega squared r. And let me, you know what, let me move these over to here. So we'll say AT is equal to alpha r, and AN is equal to omega squared r, right? Which is super friendly if everything is in 2D world and we're able to just deal with planar mechanics, which, you know, super nice, and most of them would be that way. But at first, right, we're going to work through some problems that are going to be mathematically intense. So, and then you'll be asked for the total acceleration, and then you just do the Pythagorean, right? Because recall that we have two directions, right? So we have the n direction here. This is n, this is t. And so if we're talking about the total acceleration, then we're talking about the resultant. And so a in 2D world here is an squared plus at squared. Getting these two values tends to be the part that is tricky. So if we just start with the relationship of these, but treat them like vectors, then we can see that a is equal to a n plus a t, right? Vectors. And when we want the magnitudes, then we do this stuff. Well, picking these apart one at a time, then let me look at my notes real quick. Where we're going to end up, let's just skip to the end of this. This is kind of a bear, and what it is that this is omega times r plus omega cross, and I'm sorry, not times, cross r plus omega cross, and I write this always as v, right? And then just notice all of these are vectors. And then the expansion of this looks like this. And this is a way that you'll see it in the beer book. Plus omega crossed with omega cross r, right? But this is v. And if all of these are vectors, then this is v. So this is the bear cat. This is the one that is tough to find. And it's not that it's tough to find, right? It's just it tends to be a lot of work. And the important thing to remember is that as you're going through this, and I'll do an example a little bit later on, omega is sometimes tricky to find because if you're just given some, I think one of the homework problems says, from this point of view, it is rotating like this, and then you need to define the axis, and then define the rotation, and then define r, and then you can do the calculations, and it's not too bad. So that is, let's see, I think for now that is a good place to take a rest. Make sure you got all of this down, and that you at least understand sort of conceptually how this works. And let's look at this example problem. and we'll start putting a little bit of this to work. Not the tricky stuff just yet. We'll save that for another video. But let's take a look at this example problem. So the situation is that a cord is wrapped in this guy, and a force is applied to it such that when the force is applied, it results in an acceleration of 4t meters per second squared in this down direction. And excuse me, everything starts from rest, and we are asked to find alpha as a function of t, and b, theta as a function of t. So first things first, we know that a, remember p, in the tangential direction, right? What is that? That is alpha r, right? Because we're in the 2D plane now. Alpha r. So we have a, right? That is this guy here. And we have r. R is 0.2. So we just rearrange. And alpha is 4t over 0.2. Let's see. 4 divided by 0.2 is 20. So this is 20t. And welcome to the world of you have to define the positive direction now on pretty much every problem. So just get used to adding a symbol like this somewhere on the page so that you're defining positive. And this is rads per second squared. I usually write rad per second squared, that way I don't get confused about the s, but not sure. Okay, and then remember that alpha is d omega dt, right? And we can differentiate that, and what we get is omega, right? We can expand it, but it's well, here, let's go ahead. So it's d omega is equal to alpha dt, right? And we need that because we have a t in the in alpha, right? So we'll integrate here from omega naught, except that omega naught is 0, so we'll just say 0 to omega. Save ourselves a couple of lines here. And from here, we're going to integrate from 0 to t, and so what do we get? We get omega is equal to 0 to t and 20t. So when we integrate that, it's 2. So let's see, well, dt equals 10t squared from 0 to t, so 10t squared, right? Okay, all right, and still we're there. Okay, well, that gave us the, let's see, did I write down the problem wrong? I may have. Angular velocity, yes, I did. Right, that doesn't make sense. This was not, they weren't asking for the angular acceleration, they were asking for the angular velocity. They gave us the acceleration. Okay, so this is what we wanted. Okay, and so for B, we want theta as a function of time, right? Well, what is omega except for d theta dt, right? And using the same strategy, then we're going to end as we did up here. This is going to be what? What do we got here? D theta and then omega dt, right? So d d theta will go from 0 to theta, so this will be theta. It's going to equal the integral, and now we've got 10t squared dt from 0 to t, right? And what is that? That is 10/3 t cubed, right? There we go. So theta as a function of t is 10/3 t cubed, and omega as a function of t is 10t squared. Okay, well, I hope that was helpful. I promise it'll get more interesting, and I will see you in the next video.